Sorry about that. Thanks for reporting it, Catherine. So we need to define a loss function. If the original loss function that we have defined in the context of the problem that we are solving, if that's differentiable, that's all fine. However, that's not necessarily the case always. So in the case of classification, 0, 1 loss is the loss function that we want to minimize. However, the loss function is not differentiable because it's all, if you look at the derivative, it's all 0 almost everywhere. It's 0 almost everywhere, except for at one point, that is when the input to this loss function is 0, that is the infinitely large. Infinitely large or infinitely small, it doesn't really matter as long as it's not continuous, right? So in that case, we need to find a differentiable proxy to the loss function. In the case of the classification, we looked at the log loss function, we looked at the margin loss function or the hinge loss function, and then we talked about how we can come up with infinitely many possible proxy loss functions that are going to be a tight upper bound to the 0, 1 loss function. Sounds good. And then once we talked about the log loss, we realized that the log loss is really nothing but trying to maximize or minimize the negative log probability of the correct class given input. And then we try to look at the average across the data sets. Okay, that's fine. So let's say we now have a differentiable loss function. Once we have the differentiable loss function, then we compute the gradient, right? And why do we compute the gradient? Because we want to compute a local update of the parameters of a model or our machine, right? So at the end of the day, what we want to end up with some kind of machine that solves a problem for us. And then we need to figure out how to build this machine. And then how we are going to build this machine is by looking at the data and then looking at the loss function. And based on these two, trying to compute a local update of the parameter to minimize this loss function slightly. And then we apply this local update over and over. So that's what we did. And then when the loss function was differentiable, what was this local update? Local update was the gradient. The gradient of the loss function, so differentiable loss function with respect to the parameters. So this is what we computed. And then once we have the gradient, what we can do is to simply change our parameters so along the direction of along the negative direction of the gradient. And by doing that, we know that this loss function is going to go down slightly. And then after the parameters are updated, we're going to recompute the gradient of the loss function with respect to this parameter at this new point in the parameter space. And then we apply it over and over until we notice that the loss function does not go down enough, or we always stop. That is, we check the validation loss function, and then we stop when the validation loss function does not decrease any further. Okay, so this is how we have been actually solving all these problems. Of course, on the way, we looked at various, let's say, variants. For instance, in the case of k-means clustering, we had a part of our machine that is a z, the code vector that is not continuous. The code vector in k-means clustering, that is a cluster assignment, is discrete. So we cannot compute any gradient of the loss function with respect to those discrete variables. So we had to come up with a scheme called coordinate descent algorithm in order to minimize this objective function with respect to both the weight vectors, which are continuous, and the code vectors, which are discrete. And in the case of, and this was extended into the expectation and maximization algorithm. And then that one also was found to be coordinate descent. So, we've been learning a lot of different algorithms to minimize the loss function, but in the core, this core of machine learning that we have learned consists of two stages that we just talked about. First, define a differentiable loss function, and then second, compute a local update that is the gradient of this differentiable loss function with respect to the parameters, and then iteratively update the parameters of the machine so that eventually we end up with a machine that generalizes well to unseen examples. All fine. But today we are going to look at a slightly different setup. That is, what if our loss function is not differentiable? Loss function is not differentiable, and we cannot find the proxy, differentiable proxy to that. Not find differentiable proxies. And then surprisingly, this is not really the unusual scenario. Why is that? So for classification in particular, we were able to find a nice differentiable proxy to the 0-1 loss. But if you start moving into any arbitrary loss function, it turned out it's not really easy to come up with or design a systematic way in which we can design a differentiable proxy. In other words, finding a differentiable proxy to the loss function or the non-differentiable loss function is more of an art than science. We need to, in fact, think about the problem carefully. And then for every problem or every non-differentiable loss function, we have to come up with a unique proxy to that. And that's not that great, right? So what we want is that we want to know if we can, in fact, minimize this loss function that is not differentiable directly. That sounds kind of difficult. However, it turned out that that's not really impossible. So let's just try to write down what our objective function is. And in this particular case, for the reason that I'm going to discuss a bit later, we're not going to think about the loss function, but we're going to think about the reward function. And then we're going to use R to indicate this a reward. And in the case of the reward, unlike loss, we want to maximize it, right? So what we want is that if we want to solve a problem, so we're going to compute the expectation over the data, right? So X is going to be from the data. And then we want to look at the reward. So there's a Y hat. Y hat is going to be a prediction from our model. And the Y star is going to be the ground truth or the correct answer. Now, interesting thing here is that although for any loss function that we looked at, we had always the target that we want to match the prediction toward. In this particular case, there's absolutely no reason we need to work on that, because whatever the prediction there was, we have a non-differentiable black box reward function that tells us whether the prediction was good or not. And then the black box function that we have no idea how it's implemented can have its own way to tell what is the correct thing to do. So in this case, we're going to simply remove this Y star, the correct answer, because there may not be the correct answer to start with, right? And then rely only on the prediction. So what is the reward we are going to get when the model predicted Y hat given this X? And then we want to maximize this expected reward with respect to theta, that is the parameters of our model, where Y hat is going to be the outcome from our machine, that is F. So we're going to work at this very abstract level. We now know that we can work in this kind of abstract level, right? F could be radio basis function network, could be support vector machine, could be logistic regression, or whatever you want it to be, right? It could very well be the k-means clustering as well. Maybe F is just returning us the cluster index or the cluster assignment for the input X given the parameters, which consist of the cluster centroid. So we know that it can be anything. So we're going to simply say that we have this F that is differentiable with respect to theta. That's what we need, right? Okay, so this is the problem that we want to solve. It turned out that solving this problem is next to impossible. It's very, very difficult. So instead, what we want is that we want to relax it. And relax this problem by making it probabilistic. So relax it by making it probabilistic. What it means is that as we have talked about over and over throughout this semester, and then once in a while, we looked at a very, very detailed probabilistic treatment of the various algorithms. For instance, we introduced a mixture of Gaussians by making k-means probabilistic. we looked at the Bayesian linear regression by making linear regression probabilistic. And in all cases, what was assumed was that the output of f of x and theta, so our machine, was the conditional probability. Right? So it was a p of y given x and theta. So what is being returned by our machine is the conditional distribution over the output given x, the input, and the parameters theta. So this is the thing that we had to work with. And then if you're unsure where this comes from, please go back to the Bayesian linear regression lecture note, and then you'll see exactly the same thing there. Now, what it means is that once we have this distribution, then we can rewrite the whole thing as trying to maximize. So we want to still solve the maximization problem. And then we're going to solve it over all the data points that we have. But then instead of looking at a single prediction from our machine F, we want to look at all possible predictions from our machine. And then those all possible predictions are going to be weighted by the conditional probabilities returned by our machine F. And then we want to look at over all those possible outcomes from our machine, what is the average or the expected reward we would get. So this is the distribution that is output by our machine. And then we look at the expectation over that. And then the expectation, and then what do we look at the expectation of? That is the reward. So I don't need that here. So what's the difference between these two things? The difference is that in the first one, the original formulation, we assume that our machine is going to return us a single prediction. That is single best prediction, and then we look at the reward of the single best prediction. In the case of the new formulation, the second formulation, our machine is not giving us a single best prediction, but it gives us all possible predictions, but for each prediction, it gives us some kind of score. And then the score is the probability. And then what we do is, instead of looking at the single best score, we look at the expected reward under the conditional distribution returned by our machine. So now and then looking at this, it's all kind of similar, right? So the R, the reward function that we want to maximize, that is the opposite of the loss function, is still not differentiable. So we cannot really easily compute the gradient of this reward function with respect to this theta. Only thing that we have changed is that we're going to look at every possible output values instead of the single best output from our machine. So how does this actually make any difference? It turned out that this kind of relaxation or the smoothing allows us to compute the gradient of this whole thing, that is the expected reward, with respect to our model parameters. And this involves a very interesting technique called the Low Derivative Trig. And then we're going to look into it, but before doing so, what we're going to look at is that we're going to look at only a single term inside the outermost expectation. Why is that? Because the outermost expectation is simply there for us to compute the average of the inner term that is our reward function across the training examples, right? So, and then we all know that we are looking at the decomposable loss function. If you remember from the very first lecture that we talked about, where the loss function or the reward function in this case is computed for each example independently from all the others. And then once the computation is done, we look at the sum or the average of it. What it means is that if we could compute the gradient of the reward of the loss function for each individual training instance or the example, then all we need to do is do that procedure or apply the procedure to every single training instances and then average them. And then you get the gradient of the total loss function or the reward. So we're going to look at a expected reward in our case of a single instance. That is this term. Let's see. Okay. And then we're going to, for now, assume that the y is discrete. That is, the output from our machine is going to be categorical. So there are many possible values y can take, and then f is going to tell us about the probabilities of all those possible values. Now, let's try to write this down. So what we want to do is that we want to compute this expectation. And this expectation is just a summing over all possible values of y. And for each value y, we look at the product of the probability output by our machine assigned to that value of y, and the reward associated with it. This is just the expected reward. I just wrote the definition of the expectation. And if I wanted to look at the gradient of this expectation with respect to theta, it turned out, because it's just discrete and finite, we can swap the order of the summation and the gradient operation here. And now what we end up with is that we can rewrite this as sum over y, p of y given x, theta, gradient of the log p of y given x and theta times r y. Now there is an interesting trick going on here, right? So we started from the gradient of the p of y given x and theta, and then suddenly that term became the p of y given x and theta times the gradient of the log p of y given x and theta. So how did we get here? What you notice is that it's a very neat trick called the Low Derivative Trig. So if you remember, what is the derivative of log of x? It's 1 over x. And then what it means is that we can now rewrite things a bit. Okay, let's actually write it slightly differently. That's going to be easier to understand. So what is the derivative of log of f of x? It's going to be 1 over f of x times the derivative of f itself, right? And then now what we can do is we can now move the denominator from the right-hand side into the left-hand side. That is, we're going to have f of x times log f of x, and then we have the derivative here, and then that's going to be derivative of df. And then here, f of x is going to correspond to, so f of x corresponds to p of y given x and theta. So since we are looking at the derivative of the p of y given x and theta with respect to theta, there is the f prime of x. We can replace this with the f of x times, so that is the p of y given x and theta times the gradient or the derivative of the log of f of x, that is a log of p of y given x and theta. And then the nice thing is that what this means is that we computing this gradient of this expected reward is same as computing the expected gradient of the log of p of y given x and theta weighted by the reward. So let me rewrite it here. So I'm going to put the r here first before writing the actual gradient. So this is how we can write it. Because, why is that? Because we have the p of y given x and theta outside, meaning that we are computing, in fact, the derivative expectation of the remaining terms. And then this remaining terms corresponds to computing the gradient of individual outcome, or the possible outcome, and that is weighted by the reward. Now, looking at this, you should actually feel a bit, some kind of deja vu here, right? What is it? This looks very familiar. This term simply says that you can increase the log probability of y. So given x, the second term tells us to increase the log probability of y. Why is that? Because the gradient of the log probability of y is telling us how to change the parameters in order to increase the log probability of y. Of course, this is a weird thing to do if you only have this one. Why is that? Because we are going through all possible values of y, and then we're trying to increase the log probability of y. That doesn't really help us. Now that's where the first term comes in. This first term tells us which values of y is more important. What does that mean? So we are looking at the reward. We are looking at the reward given to a certain choice of y. If the reward is high, we want the log probability of the y to be high. If the reward was small, we want the log probability to be low. And then we're looking at this expectation, right? So we're going to look at all possible ways in which we increase the log probability of each and every value of y. So for each value of y, we are computing what we should do in order to, what we should do to the parameters in order to increase the log probability. And we get that for every possible y value. But then instead of simply computing the average or the sum of them, we are going to reweight them. We're going to weight them by which value of y leads to higher value of the reward. So whatever the value of y that leads to the high value of the reward, we are going to move our parameters along that direction more. And because our output is categorical, what it means is that by moving along the direction, that's going to increase the probability, log probability of a y value that led to a highest reward automatically implies that all the other probabilities are going to go down. Why is that? Because the probabilities in the categorical distribution have to sum to 1. You cannot increase the probabilities of everything altogether. They have to sum to 1. So it turned out that we can compute the gradient of this expected reward, where the reward was not differentiable, with respect to the parameters theta in this relaxed formulation by using so-called log derivative trig. So I'm going to write the name here. So this is called log derivative trig. Using this log derivative trig to compute the gradient, and then the gradient turned out to be the expected gradient of the log probabilities of y weighted by the associated reward function r. Okay, so far so good. Now, unfortunately, it turned out that computing this is a bit problematic. Why is it problematic? Because what it says is that in order to compute this exactly, we need to try all possible values of y. And then we need to get the reward from all possible values of those y's as well. Now, why is that a problem? In classification, it's not a problem at all. In fact, in classification, you end up exactly what you want. Let's say we want to use the 0-1 loss. And then our reward function is going to be the inverse of the 0-1 loss in a sense that if the output y, so if the output from our machine is correct, then reward is going to be 1. If y is incorrect, reward is going to be 0. What it means is that this whole thing ends up being the gradient of the log probability of correct y given x and theta. And then that's precisely the gradient of the log probability of the correct answer. And then that's what we learned. That's the log loss that we learned about, right? So that's fine. However, in a most generic sense, we cannot assume that we can try all possible values of y and then receive the rewards from all those values. For instance, what would be an example of, let's say I want to build a self-driving car. My machine is going to look at the situation surrounding it, that is the context, and then it's going to output whether it should go to left or right. And then once the model decides whether to go to left or right, then it's going to, in fact, turn the steering wheel accordingly. And then based on what happens afterward, receives the reward. Now, in that case, you cannot, in fact, try both left and right turns simultaneously and get the rewards from both of them. Once you decide, excuse me, once you decide to go to the left or to take the left turn, you get the reward, but you cannot undo your left turn and then try the right turn in the exactly same scenario and then get the next reward. Why can't we do that, right? What if left turn actually drove your car off the cliff? And then you're going to have a irreversible damage to your car, and then the car just cannot come back and then retry the right turn. So what it means is that computing this expectation may not be doable because we are considering a generic scenario where we cannot assume that we can try all possible values of y in order to get the rewards and then compute this expected value. Now, of course, that does not mean that this is not useful. The fact that we wrote it down as an expected weighted gradient means that we can now use the Monte Carlo approximation. Monte Carlo estimation, where we're going to sample from this y given x and theta, that is the output from our machine, and then use that sample to compute or approximate this expected value. And then we're going to say that we're going to use a single sample. So Monte Carlo single sample estimate is going to be simply Ry, I'm going to use hat here, times the gradient with respect to theta of the log p of y hat given x and theta, where y hat is a sample from y given x and theta. So what it means is that we can just try one thing and then get the reward, and then look at the log gradient of the log probability of choosing the specific y, and then update your parameter accordingly. That sounds like a pretty nice thing to do. Now I'm driving and I need to decide whether to turn left or right. I'm going to simply ask my machine, okay, what is the probabilities of turning left and turning right? They should sum to 1. And then all I need to do is toss a coin and then decide which one to go to. Now, based on that, I choose one. I take, for instance, the right turn, and then I receive the reward. And then based on the reward, I'm going to reweight my gradient of the machine for choosing the right turn with respect to the parameters, and then change my parameters accordingly. And I do that over and over, right? So as I drive along, I'm going to do that over and over. And then by doing so, I'm going to, on expectation, over a lot of trials, increase the expected reward. So that sounds good, except that this is a horrible idea. This turned out to be a horrible, horrible idea. And then now here comes a concept that we haven't had time to actually discuss, that is called the variance of the estimate. So what it means is that we need to look at the variance of the estimate. So one thing we know about the Monte Carlo estimation, so the Monte Carlo estimation here, so that is, instead of computing this expectation exactly, we're going to sample a few trials from this distribution over which we compute the expectation, and then simply compute the average of the quantity that we wanted to compute the expectation over this finite set of samples. We know that this is so-called an unbiased estimator. What does that mean? What do I mean by that is that to make it a bit easier, I'm going to omit some of the things. So instead of R of Y, I'm going to just use R. Instead of the expectation over Y given X and theta, I'm going to simply just use the expectation, because we're not going to compute the expectation over any other distribution, nor we're not going to compute the reward over any other value. And then of course, I'm going to not write the theta there as well. And then I'm going to simply write it as gradient of the log of p. Of course, I'm going to compute the log of p of y given x and theta, but it's going to be the same every time. So what it means is that the so let's just use g star here. So this is the correct exact gradient. And then one thing we know is that if I compute this single sample estimate, and then if I look at the expectation over y hat this time, because I'm using just a single sample, so you can think of it as I'm going to compute this estimate as the approximated gradient or the gradient estimate using single sample, and then I can again look at the expectation of it. And then one thing I know is that this is going to be G star as well. So what this is telling me is that, okay, this is an unbiased estimate. So if you tried it over and over, if you're trying to compute this one sample estimate over and over, then you know that on expectation, you're going to compute the exact, let's say, gradient. That's what it means by what it means by the unbiased estimate. So that's fine. And then you always want to work with the unbiased estimate. Well, not always, but generally you want to work with the unbiased estimate because you know that on average over time, you're going to do exactly what you thought you're doing. That is trying to compute the exact estimate. So that's good. And then here, we actually notice one very interesting thing. Let's look at this. And then again, I'm not going to write the y hat here because that's unnecessary. I'm going to subtract some constant b. Doesn't have to be exact constant. And then I'm going to use log p. So let's try to write it down. And then what I can write down is that it's going to be r gradient of the log p minus expectation over b gradient of log p. And then what do I know? This is G star. That is the correct unbiased gradient. Okay. And then the interesting thing is that this term is 0. What it means is that if I subtract any b that is not, no, actually, let's write it once more. As in this term, I can write it as b times the expectation of gradient of log p. And then this is just 0. So what it means is that as long as I subtract some b that is not a function of y hat, because if the y hat b was a function of y hat, I cannot take this b out of this expectation. However, I did it. So what I'm assuming is that the b is not a function of y hat. As long as b is not a function of y hat, I can subtract this b from r, the reward, however I want. And then I end up, I see that this whole quantity, this expected quantity is still the exact gradient. In other words, reward is a very arbitrary concept. In the case of classification, when we thought about the 0-1 loss, 0 meant that we missed something, 1 meant that we got this one particular example correct. So it had a meaning. But the reward that we are talking about is arbitrary. Let's say I decided that, okay, so if my car made a correct turn, it's going to get the reward of 100. If my car made an incorrect turn, I'm going to give my car a reward of -100. Where does that 100 come from? It's pretty arbitrary. What it means is that as long as we are consistent across all possible values, that is that the change in shift in the reward function is constant across all possible choices. That is, instead of using the 100 and -100, if I decided to use, okay, 200 and 0, then it's constant across the choice of the turning right and turning left, because I simply added 100 to both of them. Then on expectation, the gradient that we're going to get is exactly the same thing. So we can subtract whatever we want. So we need to look at why that is the case. So we need to look at this particular term. So let's look at this particular term. Oops. Then what we know is that okay, it's a summation over all possible y, and then p of y given x theta, and then gradient of the log p of y given x theta. And then we used exactly the same technique that we use in order to derive the gradient of the expected reward. That is a low derivative trig. Because of the low derivative trig, what we end up with is that the summation over y of the gradient of p of y given x and theta. And then because y can take one of the finitely many values, we can now change the order of the gradient and summation. So it's going to be a gradient of the summation over y of the p of y given x theta. And then what is this? This is simply 1, right? This is one of the most fundamental properties of probability. That is, the probabilities of all possible discrete values should sum to 1. And then what is the gradient of 1? That is a constant, is 0. It's all 0 vectors, or the 0 in this case, right? That's why it's 0. And then that answers the question by Carlo. Okay, so this is good, but why are we actually looking at these quantities? So we are actually going to talk about why it's important to look at this particular quantity rather than the original one. And then that comes from the variance of the estimator. So this was the bias of the estimator. And then what it was telling us is that the bias is 0. That is, on expectation, this one sample Monte Carlo estimate of the gradient of the expected reward is going to be exactly the true gradient of the expected reward. However, now we can think about the variance, right? And then in particular, because this is a vector, we want to look at the trace that is a sum of the diagonals of the covariance matrix. And then that one can be written down as we're looking at the expectation over y given x and theta, and then g star is the correct gradient, and then that is the expectation mean, right? So minus, so my reward minus b. So we're going to look at this subtractive reward, gradient of the log p. And then we look at the squared norm. So the squared norm of a vector is same as the trace that is a sum of all the diagonal entries of the covariance matrix, assuming that this vector is standard. Now, the vector is this. So we want to look at this vector's covariance. But then this vector is not really centered. So we need to subtract from this vector the expectation or the mean of this vector. And then we know that this expectation is going to be G star because Monte Carlo estimate of the expectation is unbiased estimate. So this quantity is going to tell us, okay, how much variance is there by using a single sample Monte Carlo estimate instead of the exact estimate. So what does it tell me? So it tells me that by sampling one y and then computing this gradient of the low probability of that y weighted by the reward, how much difference on average do I expect to see from the true gradient that is a G star? And then we want that difference to be as small as possible, so that every time I sample one and then compute this Monte Carlo estimate of the gradient, I know that this gradient is close to the true gradient. Of course, every time the difference can be really, really large. But as long as those differences cancel each other out, then over time, you end up with the exact thing. However, what we're talking about now is that we want also this kind of changes every time to be as small, or the deviation from the true gradient to be as small as possible. And then this trace of the covariance is what tells us that deviations or the amount of the deviations are. So let's write it down. So it's the expectation of the square norm of the true gradient plus r minus b squared, the square norm of the gradient of a single, let's say, sample's log probability minus 2 times R minus B, and then that's the gradient of the P transpose G star. And then this expectation applies to the entire place. Now, G star, the square normal of G star does not depend on Y, right? So this one comes out, and then we need to now look at the expectation over the R minus B square norm of the gradient of the log probability minus 2 expectation of the R minus B times the gradient of the log P transpose G star. And then interesting thing we noticed is that this term is exactly G star by definition, right? We already showed that the expected gradient of the log probability of Y weighted by the reward is G star. And then we show that we can in fact subtract any B that is not a function of the Y hat from R, and then we still end up with a G star. So what it means is that this is just G star. And then what we end up with is the minus the square norm of the gradient plus the expectation of the R minus B star squared, and then log P squared. And of course, the square norm of the G star, we cannot do anything about it, right? That one is just given. How is it given? Because it's given by the reward or the expected reward. And the reward is not the thing that we actually change ourselves. It's just given to us. So, but one thing that we can change is this B. What is this B, right? Can we choose this B ourselves? And then there are 2 cases, and then we're going to look at both cases. So one is that the constant B. What if the B is a single value that we can choose? Then what we can do is we can think about, oh, how about we simply look at the gradient of the expectation of the R minus B squared, and then square norm of the gradient of the log P. Maybe we can look at this, we can compute this derivative and then just set it to 0, right? And then it turned out that we can indeed do this. And then because of this square term here, this is in fact a convex function with respect to B. And then the optimal B in this case is going to be, it's a very interesting thing, that the R times the square norm of the log P over the expected square norm of log P. So this is the optimal B that we can compute if the B was constant in order to minimize this variance. That is, if we set this B to be this particular value rather than just 0, so the original will be just 0, then we can reduce this variance. That is that every time, how much deviation do I have from the true gradient? Now, looking at this is unrealistic, right? Why is it unrealistic? It's unrealistic because in order to compute this, we again have to try every possible values of Y and then get the reward for each and every one of them, which was the precise reason why we were using the single sample or one sample Monte Carlo estimate. So this is unrealistic, but in practice, it turned out that all we need to do is to minimize this term for every case. So what is the case that we can, so what we do is we want to compute the partial derivative of the expected deviation of B from R. So we are going to simply assume for now that the norm of the gradient of the log of P is largely constant across all possible values of Y. And then that's going to be reasonable. That's a reasonable assumption to take, especially at the beginning of training. At the beginning of training, it's very realistic for us to think of building a machine or initialize our machine to output the uniform probabilities over all possible values that Y can take. Why is there a reasonable thing to do? Because at the beginning, we don't know, right? We don't know which class, to which class the input belongs. And then that's figuring that out is what we call machine learning. So initially we want to initialize, also at the beginning, we want to initialize our machine to output as uniform distribution as possible. In which case, this gradient of the log probability of any of y with respect to parameters are going to be more or less same or very, very similar, at least in their norm space. So this is a reasonable assumption to make, that is the L2 norm of the gradient of the log p of any y with respect to parameters is same. So we're going to assume that, then all we need to do is try to minimize this expected deviation of b from r. And then this, in fact, and then we want to set it to 0. And then what we end up with is b should be the expected r. Now, again, this is not what we want, what we can compute easily. But what we can do is we can do the Monte Carlo estimate here. And we can say, okay, this is, we can compute it by sampling multiple possible values of r, and then just compute the average. Now, how do we do that? It turned out that for both cases, what we want is to use the running average. So what we can do is that every time we're going to sample a single value of y, compute the reward, and then compute the squared norm of the gradient of the log p. And then we can now compute the running average. That is, in the next step, we're going to compute the exactly same thing, but we say, oh, the previous one was the sample from this current classifier or the machine as well. Then I can simply use that as if I sampled it from the current machine. And then I can just compute the average. But of course, that's not a great idea because the previous sample is not from my current machine. So what I do is that I want to discount it a bit. So I'm going to say, okay, I'm going to use 0.9 of this and then only 0.1 of them. And then in the next time step, I can do the same thing. I'm going to use 0.9 or 8 of them, let's say 0.9 of them, and then 0.1 of those two things. And then I can do it over and over by computing the running average. And in the lab session this Wednesday, you're going to see what it means to have this kind of running average. So this turned out to be one way to go, but the other way is that the b could be a function of x, that is the input. So it cannot be a function of y, because as soon as b becomes a function of y, this equality, that is the expectation of the b times the gradient of log of p is b times the expected gradient of the log p. This equality does not hold. So we have to ensure that the b is a function of x only. And then in that case, what we see is that in order to minimize this term, the second term, we need our b to be highly correlated with y. Does that make sense? So why is that so? Let's try to rewrite this whole thing. So what we have is that we have the expectation of the r squared plus expectation b squared minus 2 expectation rb log p squared. Now, what we see is that, okay, this first term we cannot control. I'm like, the reward is just given to us. We cannot really control it. This second one we can control. And this second one is very simple. We just want to make sure that the b value is going to be always closer to 0. Now, the interesting thing is this one. We can control these two, and then the third one actually tells us a very interesting story, is that what this tells us is that the correlation between r and b needs to be high. If the correlation is high, if when the r goes up, if the b goes up as well, and then when the r goes down, when the b goes down as well, then this whole value is going to be really high. And because we have the negative value there, negative sign there, then the variance will go down. So that is, we need to make b to correlate well with r. However, without looking at the actual y. If we look at the actual y, then we can simply set the b to be r, but then the gradient estimate is always going to be 0. Of course, that's the zero variance estimator. However, that's going to introduce a bias. That is, however many times we try, we will never find the exact, let's say, gradient. So what we want is that we want to find B that does not know precisely which Y was selected, but it tries to guess what this R value is. And then to do so in practice, you can make B to be a regression model. And then we learned about regression already in the linear regression, right? So this X is going to take as input X. Also, this B is going to take as input this X, and then try to predict what the associated R, the reward is, given this Y, selected Y. And then that's going to be our way to maximize the correlation between the value that is predicted by this B given X, and then the actual reward R given by the selected sample value of Y given X. So, okay, what it means is that we should choose this B very carefully, and then we can minimize this variance of our single sample Monte Carlo estimate of the true gradient of the expected reward. And then we can now use this gradient to change our parameters in order to maximize this expected reward. So at the end of the day, what we are going to end up with is R Y hat minus B of X, right? So B is going to be a function of X times the gradient of the log of P of Y hat given X and theta, where Y hat is going to be a sample from Y given X and theta that is outputted by our machine. And then this is called policy gradient with a baseline. So the policy gradient part comes from this reward multiplied with the gradient of the log probability of selecting the particular Y. And then baseline comes from this B of X. So B of X tells us about, even without trying anything, what do we expect to receive as a reward? And if our choice of Y receive the reward that is greater than this baseline, our expectation, then we should increase the probability of the particular value Y had. If the reward was smaller than our baseline expectation of what kind of reward we should have gotten by selecting Y hat in the context of X, then we should lower the log probability of the particular Y. And then that is the policy gradient of with a baseline. And then this is in fact one of the most important concepts in so-called reinforcement learning. So what is reinforcement learning? We've been learning about the supervised learning and unsupervised learning. And then what we have written down so far looks like some variant of the supervised learning. That's true, right? So it's a variant of the supervised learning in a sense that we are trying to predict something. However, no one tells us which value we should predict. All we get is access to this reward function that tells us whether our prediction is good or not. And then reinforcement learning is precisely that. In reinforcement learning, which is different from supervised and unsupervised learning, what we have, our goal is to build a classifier or the regression model that's going to observe the word. So this is the word or environment. So it's going to observe the word, and then that's going to be our X, the input. And then this classifier is going to choose how to act on the word. So it's going to observe the X, observe how the word looks like. It's going to observe it, and then it's going to act on the word by choosing one of the possible values of y. So that is, are we going to turn left or turn right? So what we do is our classifier should look at the surroundings of the car, that is the observing the world, and then needs to decide whether to turn left or turn right. And then every time it makes some kind of decision, that is to turn left or turn right, then it's going to receive a reward as well. And I'm going to use a lowercase r here, which is, you'll see why I do that. And then what you do is that of course, in this kind of loop, in this kind of feedback loop, it's not just a single step, right? You need to think about the many steps. That is, as you drive, it's not going to be a single turn left or turn right decision that you need to make, but it's going to be a sequence of decisions that you have to make. Am I going to turn right here? And then after that, am I going to turn left? Am I going to turn left again or go straight, right? This is a series of decisions that needs to be made. And then that's what makes reinforcement learning difficult, because what it means is that the possible value of y grows indefinitely. So in reinforcement learning, our objective function is the sum of all these rewards. So it's a sequential decision making. There are multiple steps of the decision. That's why we have this T. It's just like in hidden Markov model we learned last week, right? So it's not a single instance that we're going to look at, but it's a sequence of instances. And then what we want is that we want to maximize the sum of all those rewards that we get at every time step, every time we make a decision. And then the sum of the reward is going to be effectively the reward that we talked about, the capital R. And then this is non-differentiable often because the word is not differentiable. You cannot compute the gradient of the word with respect to whatever the loss function that you have, because we don't know how the word is implemented. So word is not differentiable, thereby the reward we get, or the sum of those rewards over time, is non-differentiable. And then we need to compute the expectation, and this expectation is over the series of choices that we have made. So we have the theta that tells us about, okay, what is this classifier we have? And then this theta is going to look at not a single observation of the work, but it's going to be a series of observations. And then the interesting thing is that this series of observations, in fact, let me actually remove this. Let me just move things around a bit, is given as 0 and then theta. And then this series of observations are all dependent upon the initial observation and also all the actions that have been taken by the classifier. So the state or the observation at time step capital T is going to be the result of outputting y values from the first step all the way to the yt minus 1. So there is a sequential dependencies. It's just like in HMM, except that we are not assuming too much here, right, about the Markovian property. So you can think of this as if you are having a very, very large classifier, and then that the input to this large classifier is going to be S0. S0 goes to RF, and then this F is going to output the first Y that goes into the environment or the world, and then this gives us the first reward. And then what comes out of the environment goes into our classifier, the same classifier again, and then this one gives us the Y2, and then this gives us, that goes into the environments again, and which gives us the reward for the second step. And then we can do it over and over, right, until the whole thing terminates. We're going to assume that the length is always, the maximum length of such a sequence of the decisions is always fixed to some finite value. So we're going to have the F, YT, and then go to the environments, and then we get RT. So you can think of this as having a very large classifier that takes as input the theta, that is the parameters, and then all these states, right? S0 and then S0 and S1 and so on. And then we have all these outputs, Y1, Y2, Y3, YT. and then that goes into the environment, that is the black box, and then this black box is going to give us the reward that is the sum of the per step reward. And then we want to change our classifier f that is characterized by this theta so as to maximize this sum of all these rewards. And then to do so, we can now abstract out all these details and then trying to use this policy gradient with the baseline, because we now know that that is computing on expectation the true gradient of this expected sum of the reward function. And then our choice of the baseline is going to make it work even better because the variance can be small. And then that actually does lead to the question by Carlo on the chat. How do we decide the function for b of x? Now, unfortunately, we cannot really, there's no D answer for b of x because the optimal choice of b of x depends on the reward function that we don't know how it's implemented. So what you do is that you can either go for the constant b and then track the running average of the reward over time and then trying to estimate or approximate this expectation or the expected R, or you can make b a function of x, and then now you can use whatever the regression function or the radial basis function network that you have learned in this semester to implement this linear regression so that this b is going to predict what R should be. And then you can use linear regression, you can use Bayesian linear regression, you can use a radial basis function network. It's all up to you. And then it's very usual these days to use some kind of deep neural networks there, but it's not really necessary. So what this tells us is that we can, even though most of the things that we have learned throughout this semester has been confined to the case where the loss function was designed to be differentiable, but the whole framework can even work with the case where the loss function is not necessarily differentiable, because we know how to relax the whole problem by looking at the expected loss or the reward with respect to the output or the conditional probability distribution output by our classifier or the regression model or our machine in general, right? And then we know we have just learned today a particular way to compute the gradient or the estimated gradient of the expected reward. And then that was the policy gradient with the baseline. Okay, so far so good. So that actually ends all the contents that I have prepared. So let's just try to wrap our mind around what we have learned this semester. What we have learned, in fact, covers all possible corners of machine learning except for the theoretical part. So this course has focused very much on the practical aspects of machine learning. And we covered what supervised learning is and how we do supervised learning, what unsupervised learning is and how we do unsupervised learning, especially in the context of matrix factorization. And then in the last lecture today, we learned about so-called reinforcement learning or bandit-based learning, where we have a reward function that is not differentiable and we cannot simply try all possible output because either the output space is too large or getting the reward, coring or computing the reward is not reversible. That is, once I get the reward by trying one value, I cannot retry, reset my state back, and then retry another value. In that case, we talked about the policy gradients. So it really does cover the whole field of machine learning. And then if you remember from the very beginning of this course, what was the goal of machine learning? The goal of machine learning was to build or to develop an algorithm that's going to give us an algorithm based on the data that we have provided. And then there are many different ways in which we can provide data. In supervised learning, we provide a data to this machine learning algorithm in the form of paired data sets. That is, each and every instance is going to be input and the correct output. In the case of unsupervised learning, the data that we provided was simply a set of instances without any indication on what is the correct answer to them. In the case of reinforcement learning, now we were going a bit further and then effectively telling our machine to try things out on its own in order to collect the data as well. So we're going to provide whatever the initial observation is. So we only provide the initial observation, but from there on, our machine is going to try out various things, that is by sampling from its output distribution, and then based on which it actually goes to different places or collects the different observations. So we look at these 3 different paradigms, and all these paradigms are there for us to automatically build an algorithm to solve our problem. Now, before we finish, I'd like to talk about a bit of a potential issues in using these machine learning algorithms. Of course, because we had to go through all these details of different algorithms, we didn't have much of the time to look at the actual problems. Although in lab sessions, we tried our best to give you the sense of how these machine learning algorithms can be used in a realistic setups. However, one thing that I believe we haven't really talked about is the potential problem of using machine learning algorithms that we have learned this time. Is that the main, and then there are of course many problems, but the one that I want to briefly touch upon is the distinction between causal relationship and correlation. So most of our machine learning algorithms, what it does is to look at the data, look at the observation, and then trying to figure out the correlation between some of the observation or some of the features of the observation and the desired output. And where the desired output can be provided by ourselves in the case of supervised learning, or desired output could be provided implicitly in the case of the matrix factorization, and also in the case of the reinforcement learning, desired output is not provided, but whether the selected output is good or not is provided as a form of the reward function. Now, what these machine learning algorithms are going to find is trying to figure out which of the features in the input or their combination correlate well with a good outcome, that is the desired outcome. That does not necessarily mean that the selected features or the features that are used highly by our machine are causing the desired outcome. So for instance, let's take as an example that you want to in fact build a classifier that's going to determine the success in the college admission based on the high school students, let's say, features. So you take one student from high school, and then you're going to see, oh, the student gender, let's say male, like the zip code of where they're from, blah, and then this is a score from math course, blah and blah, and then you can get all those features. And then there's a height, and then the weight and everything. And then what you want is that because you want to build a successful consulting firm for the college admission, you want to build a classifier that's going to tell me whether this high school student is going to be successful, excuse me, in this college admission or not. And then what you did was that you collected all those data from your colleagues and peers and from the high schools, and then built this classifier. And then, surprisingly, this classifier actually told us that the kids from the rich neighborhood easily go to a better college. And then, of course, what does that actually tell you? And that classifier is probably a very, very good classifier in terms of the accuracy. But that classifier does not tell us about the correct causal factor, right? The causal factor behind student going to the college because they are from the rich neighborhood is just not because they are from the rich neighborhood, but because there are other factors that are favorable to the students who are in the rich neighborhood. In other words, it is not capturing the actual causal factor. That is that you need to be competent in order to enter a good college, but it is capturing the fact that you are from that student is from the rich neighborhood, thereby they go to the college better. That's not the correct thing to infer from this kind of machine learning model. And then those are called spurious correlation. So those correlations happen because there are unobserved confounding factors that we cannot really observe from the data alone. And then in that case, if there are such confounding factors that we cannot observe, then these machine learning algorithms cannot capture those true causal relationship between the features and the desired outcome, but it's going to simply capture a spurious correlation between some of the relevant features and the desired output. So which means that we have to be very careful in using, deploying or using these machine learning algorithms and or drawing conclusions from these machine learning algorithms. I'd love to talk about all this causal inference and so on, and then I could go much deeper into this direction as well. Unfortunately, this course is called Introduction to Machine Learning course, and then there is a limited time, and then there are so many things that we need to teach you in order for you to build a foundation on top of which you'll be able to explore further into the causal inference as well as more advanced machine learning topics in the future. Anyway, that was it. So next week, as I announced earlier, we are going to have a QA session, which is largely going to be run on Campus Wire. However, I'm going to open the Zoom as well so that you can join. And noon next week, Monday, the final exam is going to be released on Grayscope. Please do make sure that you are registered on Grayscope. I have registered you all of you already, but let's make sure that you do. And then in 2 days, you will have to submit it, all the answers. Otherwise, it's going to close down. And just one thing, if you have not registered, or if you are not registered officially in the course, please do not take the final exam. We have plenty of students already for us to spend enough time grading all of them. So if you could just take a look at the exam questions, but do not submit them, that's going to be better. All right, that's it, class dismissed. If you have any questions, we are going to have the office hour of the course assistant tomorrow. I'll see you later then, bye-bye.